Earthlings, if you follow the channel, you know that we are resurrecting the Apollo communication system with original spacecraft and NASA ground equipment. We've been at it for a while, getting everything up and going bit by bit. After years of work, we've finally added one of the last remaining pieces of the setup in the last episode. And what a box it is! It's the all-important PCM digital telemetry box. The box that was measuring everything in the spacecraft and transmitting data back to Earth in digital form. And it did that at a formidable speed of 51.2 kilobits per second. Formidable for a mid-1960s design, that is, and also the distance involved. It was so much data that only part of it could be transmitted back to Houston from the ground tracking station in real time. Remember that back on Earth, they only had 2400 bits per second modems at the time. Nevertheless, that subset ended up filling the screens of Houston with lots of data. In the last episode, we successfully hooked up and powered on the PCM. We saw what looked like a good digital stream coming out, and Mike's FPGA contraption was able to decode the stream according to the complicated NASA document. It locked on the sync pattern, read the frame numbers, and successfully decoded at least the 2 test patterns. That was a very good start. Now the next logical step is to feed some telemetry input signals, see if our PCM box can transmit them, and see if we can decode them at the other end. There is one big problem though. We don't know which of the thousands of pins to use. Remember, the box is mighty. It can transmit 365 analog signals and 304 digital ones. But sadly, none of the signal input pins appear on the schematics we have. Well, let me take that back. I should have said almost none. Because Mike discovered that a few input pins were documented on one of the SCE schematics pages. The SCE, which stands for Signal Conditioning Equipment, is the famous piece of equipment that they had to switch to AUX on Apollo 12 to restart data transmission after the lightning strike, and basically save the mission.
Rolls complete.
Roger, Pete.
What the hell was that? I lost a whole bunch of stuff.
Mark 1 Bravo.
Roger, we had a whole bunch of buses drop off. There's nothing. Gang, I don't know what happened here. We had everything in the world drop out.
Roger.
I got 3 fuel cell lights, an AC bus light, a fuel cell disconnect, AC bus overload, 1 and 2, main bus A and B out.
Apollo 12 Houston, try SCE to auxiliary, over.
SCE to auxiliary. What the hell is that?
SCE to auxiliary.
SCE to aux.
ECOM reports the readings back.
Well, that's what you call a close shave. So let's take a look at the SCE drawing. The SCE sat upstream from the PCM and was responsible for scaling all the various input voltages to the standard 0 to 5 volts, which is the only range that an analog PCM channel could accept. For doing the scaling, the SCE needed a few precise reference voltages. They are shown on the drawing, and they are plus 5, plus 10, minus 20 and plus 20 volts. Of course, if the reference voltages were off, then the scaling would be off, and all the telemetry measurements would be off. So Houston kept an eye on the SCE reference voltages, also via telemetry. And we can confirm that in our drawing, the telemetry measurements appear in large circular symbols. The symbols include the telemetry code number, the signal name, its range and its sampling rate. And we can indeed see that all 4 reference voltages are sent to the PCM for remote monitoring. But sadly, it doesn't show the physical connection to the PCM box, so we still don't know to which connector and pin numbers these go. However, Mike found a different, much earlier drawing of the SCE that does show a few physical connections. And that was the lucky break we needed. We can see that the plus 5, plus 10, minus 20 and plus 20 volt reference voltages are scaled and sent to the PCM input connector J3. Aha! And hallelujah, the J3 pin numbers, or letters in this case, are also shown on the drawing. It says pins A, B, C, D, double D, double E, and double C. If this early drawing holds, which is no guarantee, then we finally have a clue about where 4 of the analog telemetry inputs are and can try to start sending actual data through the PCM. So we pick up from the previous episode when we just managed to decode and plot the frame numbers, going repeatedly from 1 to 50.
So
Alright.
I think if we feed data into it, we should just be able to plot it like this.
Mm-hmm.
And we identified finally on the, let's see, it's on the signal conditioner, the SCE page of this document has a precious few pin numbers for
For the pins,
PCM.
for the pin
There we go.
that went through it.
So we have all of these connectors and no idea what most of the pins do, but I now know what 7 of them are.
Okay.
And we should be able to feed in. So this is measurement ID CT0017V. And when you're looking at Apollo stuff, usually the measurement IDs are given in this format, but that's not the same as the PCM channel number. So we need to map CT0017V to the PCM channel number.
Ah yes, we need one more piece of info. The drawing tells us the measurement code numbers, but we don't know what PCM channels they are transmitted on. We need the channel number so we can decode the measurement from the received telemetry frame. But you know Mike, he also found a table that relates the telemetry codes to the PCM channel number.
Scientific equipment, service propulsion system. I'm looking for the telecommunications bit here. Communication and instrumentation. Okay, CT0017V. Sensor excitation 5 volts, which matches what we saw over on this drawing. 5 volt conditioned output. And that is channel code 11A119, which means that's 10 hertz data coming down from the PCM. It's going to be in the 11A group, and it's the 119th channel of that.
Alrighty, Mike has found the channel code for his SCE measurement. It's 11A119. Now we can find where in the frame it appears from the PCM drawing that we saw in the previous episode. And it's right here in byte 42 of the frame. But wait a second, there is a ton of other stuff in this byte 42. What's going on? To know that, we have to further read the letter in the gutter next to the code. It says E. Now, going to the bottom of the table, we see that E means that it's transmitted only once every 5 frames, starting at frame 4, then 9, then 14, and so on. For other frames, another measurement will be substituted instead. So word 42 is used to share 5 different measurements appearing on different frame numbers. This trick enables to send down more measurements at the expense of a lower sampling rate. In this case, our measurement will appear once in every 5th frame, reducing the sampling rate to 10 samples per second. Mike used a different reference table, but he had the same info. We should find our data in byte 42 every 5th frame. Let's try it.
So if you know the channel number, we could try putting a little bit of voltage
Yeah.
on A and B and see what happens.
So,
Make some.
You can do it with the diode check mode on the SCE.
and CT0017 is 11A119.
A lot of pins.
So pin A positive, pin B negative.
Correct.
11A119.
Are you ready?
Yeah.
Okay. Here you go.
Not seeing anything.
Could be the impedances.
It could be, yeah. It's also reading off scale high right now, which is kind of interesting. Everything, the entire box is reading off scale high
That
for all the
doesn't
analog
sound right.
channels.
Should you just ground it? See if you can get to 0?
Yeah, we could try that.
Short
Yeah,
over.
short A to D.
Yeah.
I don't know, the impedance is pretty high. It's like 55 mega ohms, which seems a little odd.
So here is the data coming out of our PCM box.
We could try a real power supply.
Yeah, we only get I have a power supply, one of the HP.
All input values above 4.9 volts will produce the binary code of 111110. So
we're thinking 11110. So
that's what this is.
So when it's floating, it's high.
Apparently, yeah.
But the grounding didn't work.
We should try putting some voltage in it.
Yeah.
Okay. Why don't we do that after lunch?
Yes, let's do it after lunch.
After a good lunch. So you just got some telemetry going?
Yeah, we have telemetry going. So all of the channels were reading off-scale high before, which is kind of weird when there's nothing hooked up to it. You'd expect them to be at 0 volts. And Eric was messing around with scoping things and connected scope ground for multiple probes to our setup over here. One of them
we had a discussion about
Right,
grounds
we were
because
talking
there's
about
different
it.
grounds in the
Right.
on this.
So if you connect the signal ground, the measurement ground, to the spacecraft ground, I guess
Things
all
start
of a
to
sudden
work.
everything went to 0 volts, and one of the channels, there's a couple channels actually that have readings that I want to look up, but we then put a voltage into the channel we were attempting to use, 11A119, and it is reading 1 volt exactly, which is what we're putting into it.
All right.
I'm plotting 11A119 coming down, so if you want to vary the voltage a little bit, we should see this plot.
So why is it coming up and down?
That's 1 bit of difference. You're seeing a little bit of ADC noise there, I think, basically.
Oh, I see. It expands the graph
exactly
to whatever it was. So what's your spacecraft side of the setup, Eric?
This wire right here is just our common ground connection.
That's
so
the
this
one
is
that
what makes it work.
That was causing us trouble.
We're also not connecting it directly. We've got a resistor in between just to limit the current, just in case.
Yeah.
So we probably don't need it at this point since it works, but you know, it's good for safety. So that comes up here into J3, pins A and B, and that corresponds with the analog channel that we're seeing.
So all
on
these
my
things
laptop.
are just inputs to the PCM, right?
That's right. They're all basically inputs. It's just lots and lots of wires going in.
So sometimes it's just a bit, sometimes it's a voltage, sometimes there's
There's-
some that are fast, some that are slow.
There's 365 analog inputs. But yeah, it's a lot of inputs to this thing.
Yeah. Let's try to put a function generator so you can see if things move around. The setup is getting more and more hairy. And so I'm telemetering a slow-moving waveform from my generator here that's connected to the ship's PCM. And Mike, you're seeing waveforms.
Seeing a sine wave come down.
And I can actually see my bits coming through. So the bottom is the signal that I'm inputting, and this is the sampling. Yeah, it looks like it's going into the next channel too. I'll change you to a ramping up sawtooth. Yeah, we're doing it.
Yeah,
Square waving.
maybe. Yeah.
Looks pretty square to me.
Okay, well, it looks like we're telemetering from the spacecraft quite well. It would be nice if we found a real fast one.
Yeah, the 200 hertz or 100.
So this is what? This is 10 hertz?
This is 10 hertz, yeah.
We've just seen how the PCM shares a single telemetry word to provide 5 channels, but at a reduced 10 Hz sampling rate. There were other rates too, which were indicated in the channel code for easy reference. The first number in the code is the first digit of the sampling rate, while the second number represents the number of zeros after it. So in this example, code 22 means the rate is 2, followed by 2 zeros, so it is a 200 Hz sampling rate channel. If you look around, you'll see that all channels starting with 1, which means 10 Hz, are in words shared between 5 measurements. Similarly, the 1 Hz channels coded 10 are in a word shared with 49 other channels. They didn't bother to write down all 50 channels and just use an arrow as a shortcut. The 50 Hz channels code 5.1 are more straightforward since they use the native frame rate. They each have a single dedicated word in the frame. But NASA also used the trick in reverse to oversample a channel. Let's look at channel 12A1 for example, a 100 Hz channel. A measurement is first transmitted in word 13, then the second one appears in word 77, which is exactly half a frame later. So the 100 Hz channels are simply transmitted twice per frame at the expense of consuming 2 telemetry words per frame. The same trick is used for the 200 Hz channels, C22A1 for example. It is transmitted in word 5, in word 37, in word 69, and in word 101, yielding a 200 Hz effective sampling rate. However, these fast channels are frame hogs, so there were very few of them. Only 4 analog ones and 2 digital ones. 3 of the precious analog 200 Hz channels were used for the astronauts' heart rates. What would it take to find the fast ones?
We just start putting voltage into all of these pins and writing down which channel moves, which is going to be a long...
So yeah, we have about 600 inputs, something like that.
Z,
Z,
little b,
little b,
D,
little d,
F.
little f.
So Mike, Eric is gone, but you guys have made tremendous progress.
Yeah, we've mapped out most of the connectors on the PCM. We started out by beeping out all the analog grounds on the connectors, and then he had the multimeter in diode check mode, so he was just going pin to pin to pin. And then I realized that the software lets you set limits for all of the telemetry points, and so I set the limits for all of them to 3 volts, such that if any of them went above 3 volts, it would violate and tell me, hey, channel 10A60 just violated. And I would get a red violation and write that down, and then he'd hit the next pin and I'd write down the next thing that violated. We found all the analog channels, or a lot of the analog channels that are 50 Hertz or slower. We have not found explicitly any 100 Hertz or 200 Hertz channels. But there are a number of channels that we marked down as trouble channels, where when he hit the diode check to those pins, a lot of channels all changed at once, and not to exactly 3.3 volts. We have a way, I think, to identify 100 Hertz and 200 Hertz channels by looking at groups on the inputs, on open floating inputs. When they're sampled by the PCM, we can tell what frequency they're being sampled at if the inputs are floating. So that's going to be a project for next time.
Yeah, there's a little glitch. Actually, maybe we can show it.
We just have to disconnect the function generator here. So we're looking at the floating input now. Each one of these dips is this channel being sampled. So we can look at the frequency of that to determine that this is a 50 Hertz channel.
You guys are clever monkeys, guys. You figured it out by reverse engineering the circuit. The circuit is incomprehensible
It truly
to
is.
modern minds, right?
But that was Eric looking at the circuit and thinking that maybe we would see a dip, and he was right. This is a schematic-ish of the primary multiplexer for analog inputs.
Right, and their transistors have too many emitters.
Yep.
And it's like TTL before the day.
Yeah, so these analog 1, 2, 3, 4, 5 are the inputs. And then this 2 high-speed gates is the multiplexed output.
And there's some core logic for sampling. Either core logic or transform. It's core logic.
It has to be core logic. It has to be when this core is flipping, it turns on this transistor.
We'll take a look at the devilish 1960s analog multiplexer circuit in a future episode. It's amazing that this analog switch works as well as it does without using any MOSFET transistors. However, the high-speed version of it did not respond to Eric's quick test with the multimeter in the diode check mode, which is why we missed all the high-speed channels. Let's repeat the test with a proper test voltage input. And what I think happens is that when you have a voltage here, use it as an input, and the transistor gets the pulse from the core logic, then the base gets set at the emitter plus 0.6 volts, and then the other emitter of the transistor gets the base minus 0.06 volts, so it gets retransmitted like this, kind of a voltage mirror instead of a current mirror.
Yep.
That's how I think it works.
Something like that.
Yeah, so what we're going to do is put in a voltage on the pins that we previously recorded as probable inputs. Right, last time we were using the multimeter in diode check mode, I think it was.
Right,
and that could interact with the input circuit.
Interesting.
Right, because it's only what, a 10 microamp current source or something?
Yeah.
So maybe it's oscillating with something else in the circuit, whereas here we're just putting in a DC voltage.
And you're putting in 1 volt.
1 volt, yes.
So I'm reading 51 on 12A1, which is 1 volt, exactly.
Okay.
So if you increase the voltage there, it should increase here.
Yeah, let's try 2 volts. So that should be 102.
Yeah.
Great.
So you found the 200 hertz pin? Or one of them?
This is a 100 hertz pin.
Okay.
I guess we could go through each of the mystery channels and figure out where to go.
So 12A1 is G.
Okay.
Our next treble pin is capital N on the same connector.
Capital N.
Yep.
So we're on capital N. Let me give you a volt. Here's your volt.
Up and on 12.
You got a 51.
22A. Nope. 51A? Oh yeah,
No.
51.
Oh, is it?
Yep, 51A2. Channel 51A2 is currently reading 51 ADC counts, which is exactly 1 volt.
Not anymore.
Now it's reading 2 volts.
Could change it back. Yeah.
And what program are you using to view it?
This is Cosmos.
So this is what you use at work?
We use an old version of this, yeah.
Okay.
So are you going to write an Apollo plugin for this?
This is I already made the Saturn V plugin for this. Now we have a PCM plugin. It can be
wow.
a PCM plugin.
Little F. 1 volt.
Okay, it's not a 12. 200 hertz. We found one. 22A3.
Do we want to hook it up to a function generator?
Yeah, I want to
High
see
rate
a
going?
200 hertz channel. I want to see a little sine wave digitized from the moon. So here we go. We just hooked up the generator over there. Whee! Right there. Well, it's such a powerful box.
It's impressive how much data it's sending down.
So we need to hook this up to a heartbeat monitor so we can get a...
I think that's what the 200 hertz channels were used for. There you go. Astro 1 EKG Axis 1 22A3. So the channel we're looking at right now is Astronaut 1 EKG.
So now we're watching. We're getting a heartbeat through it. Alright, the intimidating PCM box is getting less intimidating by the minute. Sorry for this laborious episode about discovering 600 pins, but someone had to do it. We'll continue our exploration of the PCM with a look at the weird analog multiplexing circuit that shouldn't work but does, and then it's on to trying it over the air, for which we'll need to build a phase modulation decoder. So analog wizardry awaits in the next episodes. See you then!